Hey students, welcome back. This is another edition of Kinetics. Today we're going to talk about reaction energy profile and the collision model, which is basically the Arrhenius equation. Remember, you can find more information about this, page 650 through 656. We won't be doing the mathematics of it, but there are some vocab words that we need to know here. So, the Arrhenius equation, again, we don't need to do the calculations, but we kind of need to know what everything means so we understand how the calculations could be done. So our formula for the Arrhenius equation, K, remember, is our rate constant. That's equal to A and then E raised to the power of negative E sub A over R sub T. So let's quickly talk about what each of those variables is. A is our frequency factor, and we're actually going to get a little more into that in just a little bit, but it is our frequency factor. All right, it talks about collisions and how many there are. E sub A is new to us. This is our activation energy. Our activation energy means how much energy does it take to get the reaction started, kind of like to jumpstart it, if you will. R, you have seen R before. This is our gas constant, but we're, instead of using 0.0821, we are going to use 8.314. And this has a little different label on it. It has joules per mole K. All right, but the one we use here is 8.314. T is our temp, and that needs to be in Kelvin, obviously, since that's in Kelvin. So this is our temp, and it needs to be in Kelvin. But again, you don't have to do the calculations with this. We just want to have to see how our rate constant is affected by both temperature, activation energy, and this thing that we call frequency factor. But to kind of get into that, let's take a look at what is called an energy profile or an energy diagram. So here is our example of a reaction, and this is our reaction of glucose with oxygen to form carbon dioxide and water. So if we take a look at this, all right, kind of taking a peek at this, we start with our reactants at a certain energy, and then we have our products at another energy. And remember, we talked about these a little bit in the fall when we talked about delta H. And we have a difference in energy, and so that difference is the reactants are higher than the products, which means energy must be released, so that our delta H is negative in this case because it is exothermic, all right? Put exothermic there. So that's kind of a review. We have seen these a little bit, like I said, in the fall, but now if we look at it, this little hump right here, all right? This little thing right here is our activation energy, and we would call that E sub A. And again, it's labeled as the energy for the forward reaction because the reverse of that would be true too. If we change colors here, from here to here is our activation energy of the reverse reaction. So we could be looking at this from two different ways. All right. And what we have right here at the top in both cases is what is called the activated complex. It's also called the transition state. All right. And what that is this is where all of our reactants and some of our products that are forming are really close and really high energy, which makes sense by our graph. All right. So our transition state is kind of like the medium or the go-between between reactants and products. And it's very high energy. All right, so we have to be able to reach that energy for us to have our reaction take place, which we'll talk a little bit more later. Now, frequency factor is how many times are these substances like colliding with each other with proper orientation. So frequency factor, capital A, how often are they colliding? And, well, their energy is important as well here, but that's kind of taken care of with the activation energy, but also proper orientation, which we're going to get into a little bit later in this video. Okay, but let's take a look at this Maxwell Boltzmann picture here. So this is a Maxwell Boltzmann, and we have something with a lower activation energy. Remember, this is our number of molecules, and these guys over here to this part are the ones that have enough energy to get over that activation energy. They have to have enough energy to get up over that hill. Some things that you might see is like when you're playing putt and you have that hill that you have to putt over. If you don't get it over, it'll just come right back to you, right? So you have to get it enough energy to get up and over the hill. Okay, so now if we increase the temperature like we did with this black line over here, all right, notice we have more particles that are able to react and have enough energy to react, all right? So that kind of is what our collision model talks about. Our collision model talks about our frequency of collisions. All right. And that calculation, again, we do not have to know how to do that calculation, but we just take it into a little account. So instead of A here, we have P and Z. All right. So the two things that go into the A, all right, is our P and our Z. So P is our orientation factor. Orientation factor talks about, are they lined up? And that's what the picture is below. So let's take a look at that picture below real quickly. All right. So what we have here is we have NO plus O3. And if you see in those first two pictures, they're not lined up correctly. So we will not have a reaction. So they'll just bounce off and go back to their normal stuff. So not only do we have to have enough energy, but they also have to be lined up. And we'll talk about that a little bit later with catalysts and how it helps them line up a little bit. Some of them do. So then if we look at that last picture, they're a little better lined up, and this is where we get our reaction. So it has to be about, are they lined up correctly? And then Z, our collision frequency, is just how often are they hitting with enough energy. With enough energy. So forgot my enough. With enough energy. All right. Because they still have to hit. And even if they're hitting at a very low energy, that's not enough. So they have to have enough energy in this collision frequency. And that's all we have for today. Thanks. See you next time.